Okay, let me start. I think there's a howling going on. Right. It's good that there are less and less people in the audience. I think it's about, I need about 3 more lectures to cover what I intended. And Taka-san conveniently reserved this room until July 25th. That's exactly 3 more, including this one. So I think that should be enough. Yeah, I thought we might have some summer break, but in any case, I don't need that much after the summer break. So I think I would just finish this extra set of lectures. Yeah, in July, and let's call it done. So last week, we finally came to the classification of the topological insulators and superconductors, which are free fermionic invertible phases. And in particular, we saw that in D equals 2 in Kondomat sense, I mean, 1 plus 1, and if you consider 2 plus 1, if you consider 3 plus 1, with the symmetry class DDI or D3, and in the HEP-TH language, if you take pin minus or spin or pin plus as the space-time symmetry structure, then the free classification was all given by Z. However, it's known that if you allow interactions, then this Z classification becomes Z8 in the sense that if you have 8 massive fermions, then you can add interaction terms and continuously connect it to the 0 case. Similarly, in 3 plus 1 dimensions with D3 symmetry class, this Z classification is known to reduce to Z16, whereas it's known that this 2 plus 1 D case with symmetry class D or spin spacetime symmetry, this Z classification remains. So that's known from physics arguments. And people wondered what's going on in general. So how we could deduce these answers from a general point of view. So originally, these reductions were found by explicitly constructing a continuous deformation, which changes a class 8 into class 0 or class 16 to class 0 in each classification. But that doesn't tell you, for example, there's no further reduction from further reduction to Z4, Z2, right? How do we know that these are the final results, first of all? And how do we know if we are given other symmetry class in other dimensions, what will be the answer? So the approach people took in understanding this question was to consider effective actions. On general space-time. So from now on, I'm basically switching to HEP-TH type of thinking. And we typically go to a weak rotated Euclidean spacetime and consider various effective action. So, for example, it is not very hard to understand why this Z classification will remain just Z classification without further reduction. So it's known that if you start from, say, n very massive fermions, bonds in 2 plus 1D, you can integrate out these very massive degrees of freedom, and we should have an effective action, non-trivial. So, well, if you want to compute the effective action, you need to use some kind of external field to see the reaction of these degrees of freedom. And from theoretical point of view, a convenient background field is the space-time metric itself. So you consider this 2 plus 1D system on some 3 manifold with some general metric, G mu nu. And you just consider very massive fermions. And one finds that action, the induced effective action, has the form of the Chern-Simons term. So this becomes proportional to n, and you have this omega cubed term. So this is the gravitational Chern-Simons term, where omega is the spin connection. So this fact that if you integrate out a very massive fermion, there's something still remaining, was known from the 80s, I think. So this is known in the 80s. The computation is fairly standard. You just do a standard perturbative computation of the correlation functions, and there's some non-zero result. And if you apply Kubo formula, you find that thermal quantum Hall effect. So there's a, I mean, if you have some temperature gradient, you will have a thermal flow perpendicular to the gradient. So it's an analog of the ordinary electric quantum Hall effect in the case of temperature gradient. And that is quantized, and the coefficient of that quantized perpendicular flow is proportional to n. So this is a physically measurable quantity. Physically measurable quantity. Furthermore, from theoretical considerations, this needs to be an integer. So not just under the deformation of the mass term, but even under the deformation in terms of various random interactions or arbitrary interactions, as long as the deformation is continuous, you cannot change an integer associated to that. Any function which is integer valued, which is continuous, is a constant. So this n cannot change that guarantees that this Z classification can never reduce. So that's how we can use this type of analysis to conclude that at least Z classification remains. How do we think of these Z8 and Z16 then? So to write down this Chern-Simons term, it is very important that the spacetime is three-dimensional. You can no longer write the Chern-Simons term in dimension, spacetime dimension 2 or spacetime dimension 4, but still, you can consider some non-trivial M2, two-dimensional manifold, and consider massive fermion. And you can integrate out. And you can end up with exponentiated effective action, ZF of M2, which is exponential of ISF in the Euclidean signature. And there is a more abstract argument saying that in 2D with the pin minus, this value Z effective of M2 is should be an eighth root of unity. So in particular, I mean, we pick a particular manifold, RP2. So this, you take S2 and perform the antipodal identification. So this is non-orientable. So we discussed this manifold as one of the main examples of non-trivial manifolds last autumn. And you consider massive fermions on that, because we are considering a BDI or P minus. I mean, that includes parity reversal. So you can consider it on RP2. And then there's a more complicated version of this argument, which says that the effective action, I mean, the absolute value part of the effective action can be easily changed by regularization, etc. But the phase is well defined. And it's known that the phase part of effective action needs to be an eighth root of unity. So I'm going to explain why this is the case later. But suppose, let's assume that for the moment. Then for any theory, not just about massive free fermions, in 1+1D with P minus spacetime structure or BDI symmetry, we can consider the effective action on RP2, then it should give a 1/8 of an eighth root of unity. So this should be something like exponential of 2 pi I over 8 times some mod 8 number, right? So this mod 8 number is some discrete quantity intrinsically associated to the quantum field theory you are considering. So as long as your deformation to that quantum field theory is continuous, you cannot change a discrete value, whether it's a integer or integer mod 8. It's discrete, so any continuous function valued in that discrete object cannot change at all. So that gives you a good way to label these Z8. And similarly, it's known that in the case of pin plus, you can consider the effective action of the theory on S4 with antipodal identification. So this is RP4. And there's an argument saying that this, if you take 16th power, should be 1. Then the phase part of the effective action of this 3 plus 1 dimensional quantum field theory needs to be discrete, just from general principle, and that gives you a label which distinguishes the theory as one of these model 16 choices. So that's the idea. So what needs to be done is to get a handle on the behavior of the effective action. So want to know how effective actions of, gapped phases behave in non-trivial spacetimes. And this is done, as I said, to classify interacting phases, right? But if we are given an interacting phase and try to compute these things, that's very difficult, right? So instead, what I'm going to do today is to understand effective actions of very massive, very gapped free fermions. So that might sound a bit contradictory, right? The motivation I started is that we want to understand interacting phases. And I said to understand or classify interacting phases, we consider effective actions on non-trivial spacetimes. But to compute effective actions of interacting theories is very, very hard. So instead, today we would like to warm up by considering effective actions of free fermions. But that gives us a lot of information and handle and the general idea of what is going on. And this effective action, phase part of the effective action of very massive free fermion is known in the mathematical literature as the eta invariant, introduced by Attia and Patodi and Zinger in the 70s, if I remember correctly. And it appeared in physics a couple of times since then. But at least I had the impression when I first heard of them that they are very intricate and mysterious objects. But I'd like to emphasize that this is nothing to be scared of, nothing mysterious. It's just effective action of very massive fermions. It's very computable. So maybe I shouldn't have introduced this dangerous word. Scary word. It's just effective action of very massive fermions. So let's begin. So you want to consider the effective action on some d plus 1 dimensional manifold of some fermion with mass m, right? And let me use a path integral formalism. So it's basically, I'm just going to use HEP pH formulation. And you perform the path integral over the Dirac fermions. I'm going to be very schematic, but I hope you get the idea. So the space-time action is something like psi bar psi, and the mass term plus the Dirac operator. So this is the free Lagrangian. And you perform the path integral over the fermions. So all you have to do is to diagonalize this. Diagonalize. So let's say eigenvalue of D. So Dirac operator, I didn't even add the slash, but this Dirac operator has, let's say, has eigenvalues lambda A. Then up to regularization, it's free. And Grassmann integral of exponential just extracts the value here. So it's just a product of I lambda A plus M over all possible eigenvalues. Of course, this is an infinite product. You need regularizations, but it's a standard expression. So if you have ever learned quantum field theory in the high energy physics setting, you must have seen this type of expression. And here I'm still keeping the mass finite. Now we'd like to consider, I'm using the same parameter m, letter m for the manifold and the mass, which was very bad. But, so you can consider a very large mass. So this makes this infinite product even worse, right? Because each term, each factor of the infinite product is going to diverge. So it's very bad. Instead, let's decide to take the ratio of a very, very positive mass fermion and a very, very negative mass fermion. The reason why I do this is the following. As I said last week, in order to realize massless chiral fermion, massless gapless fermion on the boundary, what we do is to change the mass parameter from large negative values to large positive values. And then you have a localized left moving or right moving chiral modes. So the existence of this chiral modes is not just because of this very large positive mass fermion. What's important is the difference of the effective action here and there. So that difference is what causes the boundary fermion. So in any case, the absolute value of the, zero of the effective action is an unobservable thing. So what matters is the difference of the effective action here and the effective action there. That's the only thing which matters. So if you exponentiate, what matters is not just the numerator, but the ratio of these two. The value at minus m and value at plus m. If you do this, things get better because you just do this product, and you can divide by m on both sides, and you get this -1. So as m becomes large, each factor inside the infinite product goes to a constant. So it's at least better behaved. And there you have a chance of making sense of it. And this makes it obvious that this is just a phase, right? I mean, absolute value of the denominator and the numerator is the same. So this is just a phase. And if we do a very bad thing of exchanging the order, so we want to take the limit where m goes to infinity, right? And of course, we shouldn't do this. But if we do the exchange of the limit and the infinite product, I mean, mathematicians often mock us of doing this exchange without any guarantee. And if we do this, then we can just take the large m limit where lambda is fixed. So this, in some sense, becomes a product of -1, right, for all a, which clearly doesn't make sense. So let's try to make sense of it at least better. So instead of using this multiplicative notation, let's consider the argument. The argument of a complex number is just a phase. So arg z divided by -m. Now this is a sum. And let's divide by 2 pi, so that this should be a mod 1 number, right? And then this is just a sum over 1 over 2 pi argument of I lambda over m plus 1 over I lambda m minus 1. All right. So let's see what this is, right? Again, by exchanging casually the limiting procedure and the sum, infinite sum, you see that for each fixed lambda a, if you make m very big, this is a very small number. So in the complex plane of lambda a over m, what you have is that you have a very small I lambda a over m, and you have -1 and +1. So this ratio is this one divided by this one, right? When lambda a is positive. When lambda a is negative, you are dividing this one with the other one. So in one case, it's very close to plus pi. And in the other case, it's very close to minus pi. And you are dividing by 2 pi. So pi divided by 2 pi is 1/2. So it's, in some sense, 1/2 times the sine of lambda a. again, in a very rough sense. And this needs to be properly regularized. So this quote unquote means that you need to regularize. In some sense, I mean, using this very large M first and then taking the large M limit is a regularization of this formal sum. But the good thing is that a general principle of quantum field theory guarantees that any regularization will give the same answer. So this is the regularization using a finite but large mass. In the original paper by Atti and Patodi and Zinga, they used a different regularization based on zeta functions. And in today's lecture, I will use even yet another regularization, which is more convenient for computation. But anything physically meaningful doesn't change with how we regularize infinity in QFT. So that's what it is. And this one is known as the eta invariant of this Dirac operator on the manifold M we are considering. So it's very abstract. So let's start with some example. So what's the simplest non-trivial manifold? So let's say MD plus 1 is just S1. So this corresponds to 0 plus 1 dimension. Okay, so this, right? And well, this might be a bit too simple. This might be a bit too simple. So let's couple this to U1 asymmetry. So the Lagrangian is d psi bar exponential of minus dx. So x is x plus 2 pi. And the psi bar partial x. I mean, it's a Euclidean version of time, so maybe I should use t. And plus a psi. So this is the action. So let's say the integral of a from 0 to 2 pi is a. I mean, so this is the definition of A. I subtract 1/2 from the reason I explained. It's clear that the eigenvalue of this Dirac operator, which is just partial t, is just lambda a. I mean, I shouldn't have used a, but the set of lambda is just all integers. I mean, eigenfunction is just Inx, right? So partial t is, I mean, I partial t is just minus n Inx. So this is the set of eigenvalues. And we need to shift this by a. And I forgot to add the master. Right? In any case, the eta invariant, eta of this IT plus A is just the regularized sum of the sign of say n plus A minus 1/2. So let's say, I mean, by using a large gauge transformation, A can be put within the range one-half. Then this number is positive or negative if n is larger than 1, and if n is smaller than 0, right? I mean, for simplicity, let's take A to be 0. When A is 0, then this runs over all half integers. So minus 3 halves, minus 1/2, plus 1/2, plus 3 halves, So these are positive, these are negative. This corresponds to n equals 1, n equals 2, and this is n equals 0, and minus 1, right? But you need to regularize this. It can be regularized in any way, but an easy regularization is to take limit with s going to 0 of summation, which is larger than 1, of 1/2 exponential plus 1 exponential of s. Sorry, I should. So it's limit s goes to 0 of 1/2. So over the positive eigenvalues, we want to add plus 1, right? Plus 1. But this, of course, diverges. So you add the convergence factor, n plus A 1/2. And for negative eigenvalues, you want to sum over minus 1, but with the same convergence factor, which is the absolute value. So I'm just using exponential regularization, where you just use absolute value of the eigenvalue itself multiplied by s. So when s goes to 0, then this becomes 1. So it goes back to plus 1 or minus 1. But we need some convergence factor. So you introduce s. But here this is negative, so we just convert it to this, right? So you easily see that this is just a geometric sum. You can sum it. It's very easy to do the computation, and you easily see that each term it behaves like 1 over s plus some constant. And the leading divergence cancels thanks to the fact that the signs are opposite and the density of the eigenvalues are the same. So the leading contribution vanishes, and you just get the finite contribution, which turns out to be minus A. So it's a complicated computation to get a very simple answer, but I just wanted to tell you that this is computable. Actually, this could have been computed from a Hamiltonian point of view without doing any computation. So let me explain that to you. So you see, eta invariant is supposed to be the phase of this fermionic system on S1 with very large mass m or very small mass m, right? So what is this? So in the Hamiltonian formalism, this is just trace over the Hilbert space of exponential minus beta h. And here I have an S1 is this identification. And I have introduced a background U1 gauge field A, but that's just an insertion of the charge U1 transformation operator in the path integral formalism. And finally, in a fermionic system, in order to just compute this trace of a thermal weight with this chemical potential, you need to make the fermion should be antiperiodic. So probably you might have heard the trace h of -1 to the f exponential beta h. This corresponds to periodic in thermal time. And trace over h without this -1 to the f exponential of beta h is antiperiodic in thermal time, right? So the reason I put this -1/2 between the holonomy U1 background field from here to there and this value A was that if you want to compute the thermal partition function without any charge operator insertion, you need to consider antiperiodic fermion. And antiperiodic fermion corresponds to having a non-zero background field here, which gives you the shift of eigenvalue. So this is for antiperiodic fermion, right? This is antiperiodic fermion. So this is the thermal partition function. Anyway, this is it, right? But here we are just considering a 0 plus 1D complex fermion. Right? So this is just a pair of fermion operator C and C dagger. And the state Hilbert space is just a qubit. Hilbert space is just a qubit where C dagger and C act as fermionic creation and annihilation operator. And we are assigning charge, U1 charge, charge plus 1, or charge minus 1. So nobody has told us what is the charge of this and the other one. The symmetric choice is to say the charge of this is plus 1/2 and this is minus 1/2. So that adding a fermion changes charge by plus 1, and removing a fermion decreases the charge by minus 1. Now we are making the mass term very, very large. Mass term is just a Hamiltonian for the C and C dagger system. So it's just that this energy difference is the absolute value of m. And it's just that when m is positive, you get this situation. And when m is negative, I mean, it depends on the convention, but you instead have this situation. So that the energy, I mean, charge here is -1/2, and charge here is +1/2. And we are making a very large m limit so that we only want to concentrate on the ground state, which are unique. Therefore, phase coming out of this thermal partition function just comes from this single state. So this is just exponential of 2 pi I 1/2 A minus, because this is -1/2, and this gives you the phase plus 2 pi I 1/2 A. And this, so this is the phase part of Z S1 plus M, and this is the phase part of Z S1 minus M. So if you take the ratio, you just get exponential. Ratio is just exponential of 2 pi I minus A. And the definition of the eta invariant was that this is exponential of 2 pi I eta of this Dirac operator. So by comparing, you get that eta invariant is really minus A. So this minus A in this very simple example of 0 plus 1D complex fermion just tells us that the charge, U1 charge, electric charge of the ground state between the positive M case and the negative M case is different by 1, nothing more than that. So we know this from Hamiltonian point of view, from this extremely obvious computation. And I just gave you a path integral derivation of this very simple fact about qubit system using infinite product and the subtle regularization. So it might have sounded very complicated, but the point is that in higher dimensions, in 1 plus 1D or 2 plus 1D, you don't usually get this nice Hamiltonian understanding, Hamiltonian point of view of understanding. But the space-time path integral computation usually relatively easily generalized, and you definitely get non-trivial effective action, which can be used to diagnose the status of the system. Right. Yes. Little a is the chemical potential. So the action, I mean, path integral was this. So you have the time derivative and the U1 gauge field and the mass term. And the little a is defined by integrating a from 0 to 2 pi dx. And this is little a. But I shift it by 1/2, just by convention, so that the eigenvalue of this thing becomes, eigenvalue of this thing is just given by n plus a minus 1/2. So it's just that if you have a modified boundary condition, I'm just imposing a boundary condition that if you go by 2 pi, you get a phase of I a minus 1/2. So that's the boundary condition I'm imposing. So when A is 0, this is an anti-periodic fermion. So it's a thermal partition function. When A is 1/2, this is periodic fermion. But when A is intermediate, that's a fermion with some complex boundary conditions. And that's path integral implementation of the insertion of this chemical potential operator for the charge, electric charge. Yes. Right. Yes. Also, I'm having one additional parameter give us a better understanding or more detailed information, right? I could have done this analysis by just for 2 values of A, 0 and 1/2, right? But that would be very, very obvious. The answer you get is either 0 or 1/2, and I would get just very confused by, just getting 0 or 1/2. What did we get? But here you have something continuously varying, right? So that gives us a better idea, I think. And this continuous variation really just is a manifestation of the fact that the ground state of this qubit system has an electric charge. So that's why I introduced A. Yes. No problem. That's right.
The kind of lambda A is positive.
Right.
Then 1 plus I A.
Yeah, that maybe plus 1. Yeah, maybe I should have reversed the overall sign might have been wrong. Right. Yeah, I think that's correct. Yeah.
Definition of eta invariant is non-homogeneous.
Standard definition of eta is just 1/2 with sign of the Dirac eigenvalues. However, these things are extremely, setting the convention for the eta invariant is very, very difficult because Dirac operator, even in 1 dimension is I partial t, right? But why do you prefer I partial t over minus I partial t? So if you change your convention by just 1 bit, then the entirety of the eigenvalue can easily get multiplied by -1. Then the definition of the eta invariant is sine of lambda A divided by 2, right? So then this thing changes sign. So it's very easy to get the sign wrong. And I did get the sign wrong. I'm sorry about that. Yeah, so depending on your convention, this could be easily end up with plus A. So if you want to be careful, there are so many things to be worried about, and I'm sorry that I wasn't very consistent in the choice of the signs. Yeah. So you are right. I mean, I missed one minus sign there.
You take all the eigenvalues.
Yes.
To get the invariant.
Yes.
This time,
Not really, because I mean, the set of this eigenvalue, if you put minus sign, is this, right?
Okay.
Then,
Okay.
so the eigenvalue is not necessarily symmetric. So in the original paper by Atiyah and Patotti and Zinger, eta was said to measure the spectral asymmetry. Yeah. So as you just noticed, if the spectrum is symmetric, then I mean this is 0 mod 1, just as you noticed. Yeah. So this eta is the measure of the spectral asymmetry. Go ahead.
In the calculation with something you write down just Gaussian integral.
That's right.
But then you are counting to the formation of time.
That's right.
And then that part reflects the large.
That's right.
But then can you do that explicitly? This is just a Gaussian integral. So
Yeah, it can be done at finite m. Yes.
okay.
Yeah.
Then you can take m to.
Yeah. I mean, at finite n, you can do this path integral, and it just gives you the partition function of this qubit system. Yeah. So you just get this. I mean, yeah, you know, it's a sum of two terms. I mean.
Even do so, you will get the same result.
Oh yes, of course. Yeah, I mean, I think if you go to any textbook on path integral of a ferromagnetic system, this qubit system is always used as the easiest example. I mean, that discussion might not have included this chemical potential term, but that doesn't change the computation that much. Right. Next, because of the reason you will see next week, we need to discuss something called Atiyah, Patotti, Zinger index theorem. This is a fairly complicated subject. So let's say we have a d plus 1 dimensional manifold with some Dirac operator. Suppose this is a boundary of a d plus 2 dimensional manifold. And so let's say that there's a corresponding Dirac operator there. In that case, you can consider the eta invariant of the boundary, right? Dirac operator. And there's a theorem found by these gentlemen saying that this is the sum of two terms, index of dn plus integral of some certain differential form. So this index is an integer associated to dn. So what happens is that index is defined as follows. So you typically in even dimensions, there's an operator which anti-commutes with gamma. So there's a gamma. such that dn gamma is minus gamma dn. Then you consider solutions to this. So this is called the zero mode of the Dirac operator. So these are eigenfunctions with zero eigenvalues. Then let's say n plus is the number of zero modes with gamma, so gamma such that gamma squares to 1 and anticommutes with dn. So gamma's eigenvalue is either +1 or -1. Number of zero modes with gamma psi being minus psi. The index of dn is n plus minus n minus. So this is the standard definition of the index. And this and the differential form depends on the choice of the Dirac operator. So I'm going to discuss exactly which differential form you find. So when there is no boundary, you can forget about this, right? And when there's no boundary, there's no Dirac operator, there's no Dirac eigenvalue, so eta invariant is 0. So this gives you a equality between the index of dn and the integral of some differential form over this closed manifold. And this is the Atiyah-Singer index theorem. So you might have heard of the name, which expresses the number of zero modes, I mean the difference of the zero modes with positive and negative chirality, as an integral of some nice characteristic class as a polynomial of a differential form. That's that. And the Atiyah-Patodi-Singer index theorem is a generalization of this when the manifold in question has a boundary. So that's one way to view as this index theorem. In that case, this eta invariant appears as the correction term in the original Atiyah-Singer index theorem because of the presence of the boundary. So that was the original motivation for APS to introduce this. In this lecture series, or today, I introduced eta from a completely different point of view. Eta for us was the phase part of the partition function or effective action over infinitely massive free fermion. So that's very physical. But the interesting thing is that object appears in this way, in this theorem. This is too general. So let me give you an explicit example where all three parts can be independently computed. And you can check the validity of this formula. And that happens to be, that happens to have a very concrete application in common condensed matter systems, which is the Landau quantization problem of a two-dimensional electron moving under a magnetic presence of the magnetic field. So suppose you have a two-dimensional plane with a magnetic flux going through some region. So usually in the Landau problem, you consider infinitely large plane with a uniform magnetic flux. And classically, if you have a charged particle, then they go around this circular motion. So you can quantize them, and you will have a number of states with the huge degeneracy. And the density of the states is proportional to the area, blah, blah, right? Here, and typically that computation is done by putting the system on a box with periodic boundary conditions. But instead, I can keep X and Y plane, XY plane infinitely large. But with a magnetic flux phi, magnetic flux B just in a finite region. So B is non-zero in this area, but B is 0 in that area. Then let's say B dx dy is phi, so this is the magnetic flux. Then the same semi-classical argument still holds within this region, right? Around here, electrically charged particles are trapped in the cyclotron motion. So you expect that the degeneracy, there's a degenerate ground state whose number should be given by basically the absolute value of phi. So let's see that. And in this case, for some reason, we get a connection to this by considering a two-dimensional, a two-component spinor, two-component fermion. So you just don't neglect the fact that electron has positive and negative spin. So electron wave function is now two-component. Right, and let's say the Hamiltonian of this system is given by partial x ax squared plus partial y ay squared plus b z xy sigma z. So this is the standard Hamiltonian for electrically charged spin 1/2 particle. So this is the crucial additional term in that case. So this is the Hamiltonian, and we want to analyze the spectrum of this operator. For some reason, we are led to consider this auxiliary object. So we take this first order differential operator. So it's the gauge invariant momentum operator, and consider this product. Some of you might remember this system if you attended the written exam of this graduate school, and for the preparation, if you have solved the previous exams questions from about 10 years ago, there was a question exactly about this. And yeah, so it was. So this is based on an old paper from the 70s by Aharonov and Kasha. It's the same Aharonov of the Aharonov-Bohm effect, and they found this nice system where this APS index theorem can be exhibited. So it's a very short paper, and I cited it from our lecture notes, and I even cited it from the problem of the exam. So you might have seen it. But anyway, so this is the operator D. So this looks like a Dirac operator, right? So you have sigma x and sigma y. So that's the gamma matrices, and these are a momentum operator coupled to Maxwell gauge field. And it turns out that this H is D squared. So if you take the square of this part gives you this, square of this you get. And because of the anti-commutation of sigma x, sigma y, you get the sigma z, and the anti-commutation gives the magnetic field. So it's a very nice. Furthermore, you have this sigma z operator, which we can also call gamma. So gamma squared is 1. So eigenvalue of sigma z is of course plus minus 1. And clearly D gamma is minus gamma D. Right? Because the only place sigma z can interfere is sigma x and sigma y, and they anti-commute. So this looks like a very simple system. I mean, so it has a supersymmetric structure. So if you have learned the supersymmetric quantum mechanics in some place, SQM is where the Hamiltonian is a square of another Hermitian operator with an existence of this fermion number operator. So this is a strange name to be used for this Landau problem. But at the formal level, if you call this gamma as -1 to the f, this satisfies exactly the a formal property to be a supersymmetric quantum mechanical system. So, I mean, many people complain to us, FTH theorists, that no supersymmetric quantum systems have been discovered, but there are SUSY systems right in front of us. And you can use the technique of SQM to analyze this system, which is exactly what I'm going to do. So you see, because H is d squared, any eigenvalue of H is a square of eigenvalue of D. Therefore, this is non-negative. So it's clear that the energy is bounded from below. So that's one good thing about SQ supersymmetric quantum mechanical system. And suppose you have a eigenstate with positive eigenvalue, right? Then, and let's say, because H and gamma commute, we can simultaneously diagonalize it, right? I mean, it's clear from this that the top component and the bottom component just doesn't interact. So you can independently diagonalize it. But the point is that suppose this has positive eigenvalue under gamma, then d psi plus has a negative eigenvalue under gamma, right? And psi minus cannot be 0, right? If it's 0, then applying d again, you get 0. That contradicts with E assumed to be positive. Therefore, this is non-zero. And it's clear because H and D commute, because H is D squared, psi minus is also an eigenstate with the same energy E. So what happens is that if you consider the spectrum is bounded from below by 0, and you can have various states, E1, E2, E3. But it's clear that, so this is gamma plus 1 and gamma minus 1. And applying D exchanges gamma plus 1 and gamma minus 1, and everything is degenerate when E is positive. But when E is 0, so it's the lowest energy state, you cannot use this argument because E being 0 means lambda being 0, means that deep psi is 0. So in this case, psi plus and psi minus can exist independently. And the number of such solutions is n plus, the number of such solutions is n minus. And the index is exactly the difference between the two. So in this case, we can actually solve this equation very explicitly. So let me do this for you. We introduce a function such that AX is partial phi over partial y. So notice that sign is, I mean, it's a bit different than the ordinary gradient, but it's very close. So this is, it says that AX and AY is the gradient of phi plus 90 degrees rotation. And from this, you see that BXY, so BZ, is just a minus Laplacian of phi. So you can compute psi given the flux. So we had this finite region where B is non-zero. Then, I mean, you know how to solve this. But the important point is that if you assume that B is zero outside of a finite region, then if you call this radius r, small phi behaves like capital phi over 2 pi log r. So the total source for this solution is B, integral of B. So that's about phi, right? And because it's a solution to the two-dimensional Laplace equation, it has this log r dependence. And well, this is a constant you need to determine. Now, we had psi, two-component psi given by this. And you rewrite it using f plus, which is this, and f minus, which is this. So I just define f plus and f minus. And if you compute how d acts on this, this exponential cancels the contribution from ax and ay. So that's why I introduced this function phi. So if we do this, d psi is 0. It's equivalent to the fact that d partial bar z, f is 0, and partial z, f minus is 0, where z is x plus iy, and the z bar is x minus iy. So you just introduce a complex coordinate on the xy plane, and the f phi, oops. So f plus is just a polynomial in z, and this is polynomial in z bar. So that's what you get by extracting this exponential dependence. So we are almost done. So f plus is something like z to some power k times exponential of phi, and f minus, sorry, so this is psi. Psi minus is z bar k plus of exponential of minus phi. Now you need to plug in this asymptotic behavior to this. So because this is log r, this asymptotically behaves like r over r to the power of phi over 2 pi. And this behaves like r or minus phi over 2 pi, right? And of course, the absolute value of z behaves like r. So the behavior changes depending on the sign of phi. Right. So say phi is negative, right? For simplicity, then this diverges, right? And multiplying that with positive power of r doesn't help. I mean, the wave function has to be square integrable. So this never, so this doesn't have a normalizable solution. So the n minus is 0. And for this to be square normalizable, k has to be smaller than the absolute value of this, right? Actually, in order for this to be square integrable, what to integrate is this, right? The r dr d theta. So this needs to be slightly smaller than the constant. So what you find is that k has to be smaller than phi over 2 pi minus 1, if I'm not mistaken. Maybe it's minus 1/2. I'm not very sure. So in any case, we found that the top power of this polynomial you can introduce is bounded by the absolute value of this up to plus minus 1/2 or something. The n plus is. I think this is true without the correction. I mean, up to something minus 1, but we are allowed to have 0 as 0 degree 0. So you need to add 1. I get this. So we got this. And why is this the APS index theorem? Why is this the APS index theorem? So here we have B around here, right? And you can consider an asymptotic S1. Asymptotic S1. So this is M1. And this interior region is N2. I just computed index N2. So we have the dn and we also have dm. We computed dm in the first half of today's lecture. We just computed index of dn, right? So eta dm index dn plus n something, right? So that's supposed to be the formula. And what we are seeing is this, right? Phi over 2 pi. Sorry, phi is an integral of f, b. But this is f. So this was the chancellor. So this is the standard chancellor. We discussed this at length last autumn. But because of the fact that this is non-compact and has a boundary, the integral of the magnetic flux is not necessarily an integer. I mean, it's a classical magnetic flux. So of course, it can have non-integer part. But this part is integer, right? I mean, it's by definition an integer. Sorry, this is a floor function, right? So there's a small difference between the two. There's a small difference between the two. And that this difference itself, right? But, integral of A around this one by Stokes' theorem is the integral of dA over B inside it, right? So this is really pi over 2 pi, right? And we computed that eta invariant dm was minus A, right? And this A is not really just the integral of this, but I assume that this A is within 1/2. I mean, what determines the eta invariant is the spectrum of dm itself. So the integer part of this A doesn't matter. So if you compute eta invariant for this, you really get this. And you get this APS index theorem. So this question of computing the Landau degeneracy in this spin 1/2 fermion system in 2 dimensions actually is the simplest case of the Atiyah-Patodi-Singer index theorem. So that's what is going on. So here are some comments. So in our application next week, we don't typically care about the integer part because what we care is just the effective action, which is always 2 pi I eta. So if you take the power exponential of this 2 pi I eta, this part drops out. So the form which matter to us is typically just this. In our case, this was just 2 pi I eta dn. D of S1 was 2 pi I integral over this of f over 2 pi. So this is what we had. So this is where we first encountered the Chern-Simons term. So you see f is almost an exact form, and this is a over 2 pi, right? So eta of ds1 is quote unquote very close to the Chern-Simons term. So S1 integral of A. I think I'm missing some factors of 2 pi in the denominator for the entire lecture today. I'm sorry about that. But you see, there's an issue. So this is a 1D Chern-Simons term. It's a very simple type of Chern-Simons term. But you see that this is a bit ill-defined because of the gauge transformation. We talked about this in February, I think. But it's kind of an easily computable quantity, right? So there's an almost differential form, which you can integrate over S1. You get some answer, but some uncertainty. On this side, you have a well-defined object. I mean, this is a differential operator, which is well-defined. You can compute its eigenvalues. And although it's an infinite sum, you can regularize, and you get this number. So this is better defined, but more complicated to compute. So in some sense, you can think of this eta invariant as the better defined, but more complicated version of the Chern-Simons invariant, Chern-Simons form. So the issue about gauge dependence is transported to the difficulty in the computation involving infinite number of eigenvalues. No. So although we use regularizations, I mean, there's no ambiguity in the answer, thanks to the general property of QFT that the final result in such cases are independent of the regularization chosen. Yeah. So on this side, there's some problem, and the problem disappears. But the price you pay is that it's more difficult to compute because you need to know the entire Dirac spectrum. So the same thing holds in the case when M is 3-dimensional and N is 4-dimensional. So in this case, as I said, the effective action here is kind of proportional to N times the gravitational Chern-Simons term, right? At the beginning of the lecture. So the correct statement is that exponential of 2 pi I eta M3 is equal to exponential of 2 pi I over integral over N4 of a certain differential from P1 over 48, where P1 as a differential form is trace of R over 2 pi square divided by 2, if I remember correctly, where R is the space-time curvature. So up to this coefficient, you just have trace R squared, and R as a differential form is just omega, d omega plus omega squared. So this is the standard relation between spin connection and the space-time curvature. So from this, very roughly, trace of R squared is d of Chern-Simons of omega, and Chern-Simons form of omega is this. So in the very rough sense, you can partially integrate this once by using this relation to rewrite P1 over 48 over N4 as the integral of N4 over d trace R squared over 2 pi squared 1 and 48, I think. But, I mean, this is M3 Chern-Simons from omega over 2 pi squared 48, right? Yes. Gauge group is the space-time rotation, so SO3 or SO4. Yeah. Space-time. So this Chern-Simons term, if you put in the Kubo formula, will give you thermal Hall conductance, the quantized thermal Hall conductance. In some sense, the gauge field for the metric is the gravity, and that is the source of the energy momentum tensor. So this type of Chern-Simons interaction in the low energy effective action gives you the quantized Hall effect. So this is kind of defined because this Chern-Simons form involves the connection itself, omega. So this is gauge dependent. By gauge, I mean the coordinate choices of M3. So this is not very well defined. There's an ambiguity under the choice of the large gauge transformation of the manifold. And not only that, you have this annoying additional factor of 48 or 24. So this is similar to this additional factor of 1/2 we discussed back in January, I think. In that case, we talk about the normalization of abelian Chern-Simons term, which leads to the quantization of the electric quantum Hall effect. And we discussed how we can divide by 2. In this case, because P1 is the natural integrally quantized object, dividing it by 48 is more difficult. So if you want to analyze this without using eta invariant, it's very difficult to make sense of this division by 48. But the point is, if you exponentiate over this, this is really just eta invariant of the Dirac operator on the three-dimensional manifold. So the problems related to the gauge dependence of the Chern-Simons term disappears if you use the eta invariant instead. So in that sense, eta invariant is a better defined version of the Chern-Simons term. Like this. Finally, before going further, let me just finish today's discussion by talking about the case that boundary, so far we consider the case when boundary is S1 and the bulk is D2, or boundary is some three-dimensional manifold and the bulk is four-dimensional. There are also cases where boundary is even dimensional and bulk is odd dimensional, like this. In this case, APS index theorem simplifies because this differential form part is necessarily of even degree. This differential form is constructed always from R or F. They have two indices. So this has even indices. So you can never integrate that over odd dimensional manifold. So this part just drops out. And typically, we only care about exponentiated eta invariant. So if you exponentiate this, this is integer, right? So this is exponential of 2 pi I times integer. So this is 1. So this becomes trivial, right? So you might say, you might wonder whether eta invariant in even dimensions is useful or not, right? It seems that you always get 1. But there's a catch. In this argument, I assume that there is an N3 such that M2 is a boundary. So if there's no such N3, you cannot use this argument. So this can be non-trivial. In other words, if you compute 2 pi I eta d2, and if you find this to be not 1, then this means there's no N3 such that M2 is a boundary. So this is another use of this eta invariant. And for example, you can consider S2 and RP2 as M2, right? And you can consider Dirac operator acting on it and consider the eta invariant. So that sounds very complicated, right? But these manifolds are fairly simple, so you can work out the spectrum of the Dirac operator very explicitly. And everybody in the physics department knows the spherical harmonics, right? Spherical harmonics on S2 is just a YLM we learn in undergraduate school. So this has L0, L1, L2, ... But Dirac operator acts on spinors. So you need to know spinor spherical harmonics. But it's very simple. On S2, at each point, you have just two-dimensional spinor, which basically transforms as L1/2. So all you have to do is to multiply this by a qubit. So the spherical harmonics consists of, I mean, if you compose the angular momentum L equals 1 with L equals 1/2, you get L equals 1/2 and 3/2. And if you do 3/2 and 5/2, So in the end, what you find is that you have two copies of doublet representation, two copies of quartet representation, two copies of 5/2, And you can compute the Dirac spectrum very explicitly. And Dirac eigenvalue happens to be just given by 2L plus 1 minus 2L plus 1, 2L plus 1 minus 2L plus 1, I mean, you know how to compute the L square acting on this, right? So it's very similar. The point is that you always have a pair of a positive Dirac eigenvalue and a negative Dirac eigenvalues. Because of this, you can easily show that the eta invariant for this is 0. So this is due to Takasan-san's observation, right? If the eta invariant is the regularized sum of sine of the Dirac eigenvalue, right? So even before taking the regularization off, I mean, the contribution to the Dirac eigenvalue from these pairs just drops out. So this is 0. For RP2, what happens is that you need to do some antipodal identification of S2. So basically, this cuts down the spectrum by half, but this antipodal identification is compatible with this SU2 or SO3 rotation, right? I mean, it's invariant of rotation. So in order to remove half of the representation, half of the spectrum, you just need to remove one out of each copies of representation. It turns out that it alternates. So if you drop the negative eigenvalues first, you need to drop the positive eigenvalues next, and then you drop the negative eigenvalues, and so on and so on. So there's a slight slight asymmetry in the spectrum. So you get positive eigenvalue, negative eigenvalue for the next eigenstate, positive, negative, positive, negative. And you can compute the eta invariant just as before. And it turns out that eta d is RP2 1/8. So this means that because eta is 0 here, it can be a boundary, right? And it is actually true. I mean, it's not guaranteed, but you know that S2 is a boundary of a three-dimensional ball, right? But if you try to do the quotient, you are forced to quotient, and there's a singularity, right? So you cannot have at least you cannot fill RP2 by quotienting the entirety of this. And this eta invariant being not 1 means that there's no way to have some smooth manifold filling in RP2. But suppose you have 8 RP2, right? 8 copies of RP2. Then if you compute the eta invariant, it's just a disjoint union of 8 RP2, right? So Dirac spectrum got just copied by 8. So this is 1. So if you exponentiate, this is 1. So nothing forbids us to, at least this argument doesn't forbid that there's no three-dimensional manifold such that it has 8 RP2 boundary and which is smooth. And actually, it is easy to construct such a manifold. So let me end today's lecture by giving you the example of such a manifold. So we start from T3. T3, right? So this has the identification x plus 1, y plus 1, z plus 1, right? Now we take the identification by z2, which send x, y, z to minus x, y, z, right? Then if you have just one direction from 0 to 1, then if you take the z2 quotient, there are two fixed points, right? At 0 and 1.5. Because plus 1.5 and minus 1.5 are shifted by 1. This means that there are actually 8 fixed points, right? In this T3 over Z2. This is singular, right? But around each fixed point, what do we have? Very close to each R3 fixed point, we just have three-dimensional space with this antipodal identification. So we have a sphere with antipodal identification. And because we are not just quotient in S2, but R3, there's a singularity. So we cannot use this. But the good point is that we instead remove these interior of 8 balls. Right? Then minus 8 balls. Sorry. I should first remove 8 balls and then divide by Z2. So this is perfectly smooth. What are the boundaries? At each of these points, you have a boundary which is S2 divided by Z2, which is RP2. So you have 8 RP2, which is nicely filled in by a smooth manifold. So indeed, so that's compatible with the fact that 8 times the eta invariant of RP2 is 0 mod 1. So this is related to the fact that the classification reduced from Z to Z8 in 1 plus 1D topological superconductor. And next week, I'd like to discuss the relation of this interacting fermionic invertible phases and Bordizan groups. So that's almost, we are almost coming to the close. So next week, I'm going to discuss the general discussion about Bordisms and interacting fermionic phases. And then the final week, I'm just going to give various examples of computation. So that's the idea. So thank you very much. Sorry for going over time, but I guess, yeah. Any more questions? Yes.
This argument coupled to the arbitrary
Yeah. This. It's done. It can be done in arbitrary dimensions. So this just means that.
I'm confused that this 8 is somehow related to the reduction.
Yeah. So this is related Z to Z8, and the fact that this 8 was that this is 2 to cube. where 3 is the dimensionality 3.
But certain things that don't happen.
In 2 plus 1D.
And there's some time on them. You say that is protected by more.
Right. So
if this kind of argument is applicable, how they are
you see the difference between 1 plus 1D and 2 plus 2D is that in the APS index theorem, in the exponentiated form, we have this relation, right? And here, when this is even dimensional, this is odd dimensional, and the differential form is even dimensional. So this was 1. So that's why I could use the fact that whether this is 1 or 0, to decide whether the manifold can be filled in or not. So in 2 plus 1D, this is odd dimensional, and this is even dimensional. Therefore, this is non-trivial. So you cannot use this argument to decide whether Z reduces to Z something. But the same argument could be used in 3 plus 1D. So in that case, I could just upgrade this to P5. Then this means that 2 to 5 RP4 arises as a boundary of this T5 minus 32 volt over Z2. So this is 32. But the argument, the reduction is actually to Z16. So it's a slight mismatch. But I mean, this is not contradictory, right? It's just that this guarantees that I could easily construct a manifold such that whose boundary is 32 RP4. There's a better manifold whose boundary is just 16 RP4. But it's just that I haven't been able to construct it in this way. So it's not a contradiction. There's no guarantee that this very special construction gives it this. So, yeah. But at least it is consistent. Any other question? Yeah, so this is deceptively simple. Everything works so well. Any other question? Turn off the recording, I guess.